Okay, so I was just on this National Academy panel that produced this pair of reports, and so I don't know how much interest there is in hearing about these reports or whether you want to hear about my research or whatever. So maybe I'll just go through some key conclusions of this. So let me just say, and I'm not supposed to talk about internal panel dynamics, and so I'm assuming there's like no, but this is being recorded. Okay. So, okay, I'm not going to talk about internal panel dynamics. Okay, so one of the things is that we put 2 reports out, and I can say that originally we were tasked with the idea of writing a geoengineering report, and I said basically that that's absurd because, if you're thinking of passive letting forests regrow on former cropland, that's so different from putting aerosols in the stratosphere that it doesn't really make much sense to lump them together, and even you could argue that it might not make sense to lump that with industrialized sort of air capture with geologic storage. And so one of my big fights was to kind of get this 2 reports, and I finally kind of won that battle, but then there was some backsliding when they stuck climate intervention on the top of both of them. And I sort of argued that carbon dioxide removal shouldn't be characterized as climate intervention because, insofar it's reducing net anthropogenic greenhouse gas emissions is actually reducing climate intervention. And so to characterize reducing net emissions as climate intervention is not really a helpful way to think about things. But with these reports, kind of group consensus activities, you can fight about some things and you can't fight about everything, and some things that you don't like you have to live with. And so, I didn't want to just, anyway, so I thought that sticking this climate intervention up here was a mistake and I didn't like it. I would have rather to see, my vote was to call this one carbon dioxide removal, and I was suggesting using solar geoengineering for that one. But anyway, that is what it is. And so this, and so basically we were trying to communicate by breaking this into 2 reports that these things need to be disaggregated and thought of differentially or differently. And then there was some sort of backsliding because it ended up sticking this name on both of them and releasing them on the same date. And so anyway, so there was some move over the 2009 Royal Society report towards separating out these 2 things, but not as extreme as I would have liked. So we were tasked not with trying to be exhaustive on everything, but to try to feature a few things. I'm going to focus on the solar or this side of things, but the main 2 features things that are focused on in the carbon dioxide removal report are biomass energy with carbon capture and storage, and this idea of direct air capture also with geologic storage. And I guess the main thing that's kind of different in this report, say from the 2009 Royal Society report, is that there's increased emphasis on ocean alkalization, the idea of weathering silicates or carbonates with the resulting changing ocean alkalinity, but it's still put as a secondary feature here, and basically the 2 case studies are those. So I'm not really going to talk about the carbon dioxide report. And Jennifer Wilcox was really the lead person in helping to prepare this report. Okay, I guess did I go? Okay. Oh yeah, there's 2 reports. In the second report, now I got it. Okay, so, and on the 2 strategies that the solar side focused on was the idea of stratospheric aerosols or brightening clouds in the marine boundary layer. And basically the feeling was that satellites in space were not technically feasible, and that surface albedo change, might be useful for urban heat island effect or things like that, but probably isn't that practical or desirable. And plus there's not that much literature, and so it didn't focus on that. And so I sort of did the first draft of this one, and when it was originally, my original draft is sort of, now I can touch this. that the first draft of this said the most promising carbon dioxide removal approaches do this, because I think you can pick something like ocean fertilization, where it has a lot of the same kind of problems that solar geoengineering has. But basically the basic idea is that carbon dioxide removal, for the most part, has a lot of similarities with what's typically considered mitigation, in that there's no big multipliers in chemistry for each molecule of CO2 you put in the atmosphere. You have to do something to get that molecule out, and so the scale of the CO2 removal effort has to be similar to the scale of the system that put it in, which means it's going to be roughly the scale of the energy system, and which then makes you say, well, maybe we should just be focusing on energy system transformation. Anyway. And the albedo modification, or which has also been called solar radiation management or solar geoengineering, basically are pretty cheap, can be deployed quickly, fast acting, and so on. And the carbon dioxide removal ones slow, expensive, etc. The ones that are scalable. Let me just talk about this nomenclature. I actually argued for solar geoengineering, because if you, every time I've given some talk, I've called it something else and not used the geoengineering word, people kind of accuse you of being a salesman and like you're trying to sell this thing, and why are you using this other euphemism when we know it's, some kind of evil geoengineering. So one of the sort of historical sort of oddities is the solar radiation management term, which was embraced by the 2009 Royal Society report, really is a phrase that I coined in 2005. We were having a meeting at NASA, which was a joint Carnegie Institution NASA Ames meeting, and the NASA headquarters got skittish about geoengineering meeting, and that they're afraid of bad press and so on. I don't really know their motivations, but there was some skittishness. And so we decided, the idea was, let's name it something that sounds very bureaucratic and obfuscatory that will pass under the radar of NASA management. And I had just escaped from a Department of Energy lab where they had like a carbon management program. And so it's sort of on the model of carbon management, let's call it solar radiation management. And like we were laughing, and it was meant as sort of as an intentional thing to obscure and sound bureaucratic. And so we were really kind of surprised that it caught on. But it was the name of this first workshop in 2005, I think it was 5, at NASA Ames. And so anyway, there are some people on our committee who felt that, first of all, that the word management implied that we knew how to manage things, and really what the proposals are around is affecting surface affecting the overall reflectivity of the planet, or amount of scattering of the planet, and so that albedo is the appropriate term. And some people thought, well, albedo sounds like Latin, and is it nobody knows what it is, and is it really the best thing to communicate to a broad audience? And so I'm still kind of saying carbon dioxide removal and solar geoengineering, but I really don't care that much. So let me just go quickly through the main recommendations of this report. And there's the first motherhood and apple pie that says we should focus most heavily on mitigating greenhouse gas emissions in combination with adaptation. So I can say that all of these recommendations were heavily argued about and wordsmithed and compromises, and I think at one point people are saying does not substitute for, and then you have economists saying, well, what does the word substitution mean? Is that what you really mean? And anyway, that's an obvious one. So then there was this is the basic carbon dioxide removal, so it's sort of saying that there should be some research on the potential to expand carbon dioxide, to research whether there's viable, scalable, affordable carbon dioxide removal approaches. And then, so then this was an interesting one. So albedo modification at scale sufficient to alter should not be deployed at this time. there's some people who sometimes read this statement. It obviously leaves open the idea that this could be revised at some point in the future, and some people you can imagine wanted stronger statements. But you could say, well, look, if you agree with a stronger statement that it should not be deployed, period, then you also have to agree that it should not be deployed at this time. And anyway, you can imagine what panels are like. So one of the keys here, there's a concern, especially among cloud physicists. Cloud physicists have done manipulative experiments in the 1990s and in the last decade also, where aerosols are introduced and you're trying to understand what the effects of natural and anthropogenic aerosols are on cloud systems, and just observing natural variability is a hard way to get at things, and so people like to do controlled experiments where you introduce things into the environment, so there's on one side there's a concern that the prospect of geoengineering is making it harder to permit those kind of, or get approval for those kind of experiments. But then also on the side of the more direct solar geoengineering side, the idea is that you might, if something's relevant to understanding consequences of solar geoengineering, well, that should be seen as a positive thing, like another reason why you might want to do that experiment, but that still you'd want to favor experiments that people want to do just to understand the climate system and relevant human dimensions. And so the idea is that things like understanding effects of aerosol influence on clouds, you want to understand that anyway, and here's another reason why you want to understand that. And so that's the kind of experimentation that should be favored in this area. Yeah, and so this was controversial, and I'm actually surprised. So let me just go through some of the wordsmithing here. It says small-scale field experiments, may be helpful, scientifically or physically helpful. And this was kind of one of the things that got picked up in some of the press accounts. And often journalists are not lawyers, and so saying that small-scale field experiments would be scientifically helpful doesn't necessarily mean that they would be helpful in some broader overall context when you include socio-political feedbacks and responses and so on. And so anyway, so even the people who think that it's a bad idea to do small-scale field experiments, the reasons why they usually think it would be is for reasons other than that it wouldn't be helpful scientifically. And so, anyway, it was interesting that this made it into the highest level as a sub-bullet on this highest level recommendations, which was seen as, and sort of reported as National Academy panel supports small-scale field experiments. But the truth of it is a little more nuanced than that, I would say. So, first of all, National Academy reports, this is funded by U.S. agencies. I should say that this is one of the things that's interesting about this report is that it was not scientist-driven. The NOAA, NASA, and the intelligence community, by which the rumor means CIA, requested that this report be done. And when this panel was announced, this rumor of CIA, which I have no reason to doubt that rumor, funding of this panel was seen in some parts as some kind of nefarious thing. But when the CIA wanted to sort of kidnap and torture people, they didn't commission a national panel on kidnapping and torturing. So the assumption, our assumption was that they were concerned about, this rogue actor scenarios. Are those something that needs to be thought about, or is that, or if there was some climate emergency, is there something that could be done? Even though I'm the last person to be a fan of the CIA, I didn't see anything particularly nefarious in their participation. Other than I see them as generally nefarious. So, Yeah, so this was another sort of big area of contention, was the governance thing. Now, there's a few things. One is we had a fair number of people with strong opinions and not that many people with deep knowledge on governance issues. And so, as often you have, this were 16 disparate people with very different views. And, so I would say the views ranged from some people thinking there needed to be a new regulatory system to other people thinking that we basically just need sort of new norms or, to promulgate norms, professional norms, and we don't really need any kind of additional governance structures or things. And so I guess we more or less punted on this whole issue and said we initiated serious deliberative process, and you can imagine how much argument there was over what words that would go there. But, it's basically saying, look, we don't know ourselves, but, it does make sense for people to think about what kind of additional governance, if any, would be needed. And so I don't want to tell you how much time was spent on this wordsmithing, but, basically the idea there should be a process that would think about what types of governance beyond those that already exist might be needed, and where there is governance needed, what is the type of research that would require such governance? And obviously some people thought there definitely is a need, and other people thought there isn't a need, and so this is like a wordsmithing that it's consensus wordsmithing. But anyway, not unreasonable. So. This is motherhood and apple pie, should be transparent, having input from a broad stake of stakeholders. I guess partly this was this issue of intelligence agency concerns that, everybody's in favor of transparency. Yeah, this one, let me just say that Granger Morgan, who is a member of the panel, has been pushing for this idea of some allowed zone and wanted clear and, thought of what's allowable to be done as quantitative guidelines. And I'm frankly not that, I'm really not that persuaded by that, but you can only argue about so many different things. And obviously to be responsive to domestic and international law and treaties, I forget what the arguments about why the word is responsive rather than acting consistently with. But anyway, it is United States. So anyway. That's more or less the main things. And so I think so what is it practically? So I think this thing about that saying that outdoor field experiments would be helpful is really scientifically helpful is important. I think the fact that the governmental agencies, NOAA, NASA, CIA, funded it and requested it was interesting. And you could speculate about what their motivations were. My speculation is that the agencies think that there might someday be money there, and they want to have their baskets ready, and putting themselves as a participant in this is probably useful. But other than that, I think in terms of scientific content, there's not that much different from the 2009 Royal Society report, which says something about the moderate pace of science, despite the large number of papers being published. So that we're sort of saying that the deliberative process should focus on stuff that involves putting material into the atmosphere, and that the sort of idea that you should worry about surface albedo change or people putting satellites in space doesn't seem very sensible. And this also, let me just say there's some tension around different things that, one of the big questions is, should you be regulating in terms of intent, in that you define something called geoengineering or albedo modification, and then anything that has that intent you start worrying about governance for? Or should it be, look, anybody who wants to put anything in the stratosphere for any reason has to go through, or above, say, perhaps some de minimis amount, or perhaps any amount, has to go through some process, and then that process evaluates the intent in weighing costs and benefits. And I was involved in the London Convention, London Protocol negotiations for ocean iron fertilization as an observer for the I'm forgetting but a branch of UNESCO. And you know, that one was very much done if you want to put iron through the surface of the ocean, what regulatory or what governance process should that trigger, and then the reason of why you want to put the iron in is then evaluated, but the triggering event is this wanting to put iron in the ocean. And it just seemed to me that it makes much more sense to trigger a process by, okay, I want to put some particles in the stratosphere, and so that should trigger a process, and then that process can evaluate my intent, and that to evaluate the intent, have your intent be the triggering thing for the process seems to me, then you need another, anyway, it just seems to me problematic. So I think this partly was mine, that this thing that focus on sort of putting material somewhere, and think about that as a framing context for how you develop governance. But anyway, if it has, this again is more this sort of Granger-Morgan kind, the Granger-Morgan idea about defining a scale. And I'm actually fine, I would be fine with something that says, look, anybody who wants to put particles in the stratosphere for any purpose has to go through some process. And if it's some tiny little amount, then there's some kind of pro forma approval. And so I don't necessarily think there's a need to define the scale of experiment which oversight begins. And the idea that there should be, governance should balance the scale of what you want to do. And so as the scale and scope increases, maybe the formality and comprehensiveness of the governance might increase also. So anyway, most of this is fairly reasonable. But again, all this is sub-bullets on saying there should be a deliberative process to consider these things. Okay, and then the last governance, you're supposed to maximize benefits while minimizing risks. That's great. Yeah, this United States, I guess this one, it wasn't meant, I see now reading it from across the Atlantic Ocean, this sounds like it could be like another Eurocentric, not Eurocentric, another US-centric saying, oh, the US should go out ahead and ignore what everybody else says. But, I mean, what it was meant was that the United States, should be engaged now. It wasn't meant to be saying it should lead. We probably should have had something more that was more international in perspective, but more the idea was to get the U.S. government to start thinking about these things. So that's more or less what the report said. I'm going to just do, so I've already gone like half hour, so I'm going to just send two short things on new results that we have. I'm going to do like 3 minutes on background stuff of why I think this is even worth looking at. And then I'll just do like 10 minutes on just 2 new papers we have coming out in the next 2 weeks. And then I'll just close there for discussion, maybe that. So anyway, temperatures are increasing. So there's this paper from 2009. It's looking at the summers, which I'm not sure how the summer's defined at the equator, but anyway, in mid-century compared to the warmest on record. And, that's something in many parts of the world, half the summers are warmer than the warmest summer on record. And, by the end of the century, I think this was the A2 scenario, that almost every summer is hotter than the hottest summer yet on record. And, I've heard different perspectives on what will happen to crops under these circumstances. Some people think, oh, we're going to breed crops that can grow in high temperatures. Other people thinking there are biophysical limits to, how much you can get crops to grow at high temperatures. But at least in the past, it's with these record heats, it's not been uncommon that they've been associated with crop failures. And so at least there's like a non-zero probability that there could be widespread crop failures in the tropics later this century. And I would say, even if that's not the expected outcome, I don't think that at this point that can be excluded as a possibility, although I'm not an expert in that topic. So then the other thing is, that again, this is an old figure, but if you take the more modern ones, that more or less if you slow, basically if you have a CO2 emission, we did a paper on this recently, the Earth heats up for about a decade and then stays hot for many centuries. And so, cessation of emissions prevents further warming, but doesn't actually cause things to cool. And so there's really no practical way for emissions reduction to reduce temperatures this century. And so if you're somewhere in here and you start having massive crop failures and widespread famines and all this kind of thing, that there could be huge political pressure to cool temperatures rapidly, and the only technically feasible way to do that is through one of these solar geoengineering things. Now, I would like to say that most of the crop models, that even the ones that predict reduced crop productivity in the tropics on in these scenarios, predict increased crop productivity in the northern latitudes due to increased growing seasons and CO2 fertilization and so on. And so, I don't think if there's an appropriate social institutional response, even in my sort of dire crop failure scenario, I don't think there's any real reason that anybody has to go hungry if there was appropriate distribution of food. And so I think one of my changes in thinking over the last couple of years is I no longer just think of sort of a climate crisis, but could be a climate crisis coupled with institutional failure that leads to something catastrophic. But I think you need both things. You need sort of the climate-driven failure and the institutional failure in order to sort of make something like solar geoengineering seem like it might be attractive. So, so this is just illustrating. We did this paper some time ago where we zeroed out emissions and the atmospheric CO2 concentration. So this is an instantaneous zeroing out emissions, and the atmospheric CO2 concentrations go down, but the temperatures remain more or less constant even after it's zeroed. And so just even zeroing instantaneously all emissions, which might, you can imagine in some real emergency thing people might do, isn't enough to cause things to cool. And just sort of as a side note, a one-time removal of CO2 causes CO2 to come back out of the oceans and land biosphere, and you end up with more or less half the warming offset. And if you want to really bring back the pre-industrial temperatures, you kind of have to keep removing the CO2 as it comes out of the biosphere and the ocean. So, obviously the big, in 1991 there was a big volcano, Mount Pinatubo, and the Earth cooled by around 0.5 degree Celsius as a result of that on the time scale of a year. And the total radiative forcing was of the same order of magnitude of a doubling of CO2, and had this, if you would have, so presumably if you sustained a layer of this magnitude, it would offset something on the order of magnitude of the amount of warming anticipated this century. And just I don't need to go through that one here. So just to get to some sort of order of magnitude numbers, so to offset the radiative forcing from a CO2 doubling, you would need, and if you were trying to do that with a satellite between the Earth and the Sun, you would need to build something around 2 million square kilometers in size, which is pretty big. So that's 1,000. So that's like a 1,000 square kilometer satellite by 2,000 square kilometer, 1,000 kilometer by 2,000 kilometer satellite, big. To do it as sort of like an orbit around the Earth, where you're covering Earth's sphere. Sphere is 4 times that because of the ratio of the Earth's surface area to the Earth's shadow area. And if you're just trying to compensate with something between the Earth and the Sun, to just increase the rate of radiative forcing you'd have to build something at the rate of 40,000 square meters per minute. And so just this idea that you can sort of build satellites or something is just sort of infeasible. But on the other hand, tiny aerosols. So what you want for the aerosols in the stratosphere, you want them to be more or less similar wavelength to light. And so like 0.1 micron particles would be pretty ideal. And that you could get that much. That's not exactly the way scattering in particles works, but even if you just took the cross-section area of a bunch of 0.1 micron particles, you could fit all of those particles into a cube less than 100 meters by 100 meters by 100 meters. And so it's not that much material. And if you thought that residence time of that was something like the order of a year, you're talking about injecting it at a rate of something like 25 liters per second, which is something that can go through a single fire hose. And, and then if you were thinking of ramping up to that over a century, the first year you just want to do 1/4 of a liter per second, which is, through a little garden hose could do that. And so, more or less, even at full-scale deployment, you would kind of need one plane, meaning a doubling CO2 kind of level of deployment. You need one plane kind of constantly emitting something into the stratosphere, which is, and the estimate of the amount of flights you would use over the year would be equivalent to like 6 hours of commercial aviation. So the costs are, in terms of global economy, are basically negligible. A direct cost, although obviously the inadvertent cost could be huge. So anyway, it could do. I'm going to run past this to show my new work because time's going on. Just to say that almost every modeling study says that this is zonal mean. So this is I don't go through all this, but basically this is for temperature change, and this is for runoff. Oh, this is for precipitation, and that basically it's not perfect, but on any kind of climate metric that you have, it reduces most climate change for most people most of the time, and basically you're reducing heat stress, but keeping the CO2 fertilization, and so crop yields, if anything, overall go up, but there's some in the models, but there's some disparity, and so if you really believed the climate models, and you didn't worry about socio-political feedbacks, you would just say, look, and you use standard kind of damage functions that are used in the crude economic models, you would just say, oh, let's emit CO2 and throw some particles in the stratosphere, and we'll have crops growing better, and we don't have to transform our energy system, and so on. But anyway, that's not my perspective. I think it's hugely risky, and things are likely to happen that you don't anticipate or want to happen. So let me just go quickly to 2 new things. So one of the things, the way my group works is we try to look for low-hanging fruit and grab it and move on. And we did the first 3D solar geoengineering simulation in 2000, and now 15 years later, there's like a whole cottage industry of it. And it's now the people who really know about particle aggregation and chemistry of the stratosphere are doing things, and so our group really doesn't have much to contribute anymore, I don't think. So we're trying to look at other things that are less explored. And so one idea is this idea of putting pipes in the ocean, and there's the ideas. One is to bring you can think of it as switching. That you're taking parcels of warm water with lots of anthropogenic CO2 and replacing it with cold water with less anthropogenic CO2. And so this was first proposed by Lovelock and Rapley in 2007 in a correspondence to Nature. And there's been 2 studies looking at it from a carbon cycle perspective. And the problem is this. There's the deep ocean waters are CO2 rich, and they're also nutrient rich, but you're decreasing the residence time of water in the surface ocean, and so there's lower nutrient utilization, and it doesn't really work very well from a carbon point of view. But there was one paper by Oshleys that looked at some thermal effects, but it wasn't with a full atmosphere model. And so this was the first simulations with a full coupled ocean atmosphere carbon cycle model, meaning CESM. And this is coming out, I think, next week or the week after in Environmental Research Letters, after having gotten rejected from several other publications, or at least not reviewed. No, rejected too. Okay. Anyway, so I don't go into too much, but we did this. We just mixed the whole global ocean down to a kilometer everywhere, and we did this both for the pre-industrial control and RCP 8.5. And RCP 8.5 is kind of a business as usual scenario. And the interesting thing, and the big surprise was this. So let's look at the dashed line, because that's the pre-industrial control. The black line is just pre-industrial control, and so that's just an unforced climate model. And when you mix the ocean down to a kilometer and keep mixing it, initially you get this huge cooling. You get something like, 8 degrees worth of cooling. But after about a half century, the planet ends up warmer than it was had you never done the pipes. And this was really a big surprise to us because it was not an anticipated result. And really what happens is because you're cooling the ocean surface. Yeah, so I don't believe model results in general unless I understand why they got those results and it seems sensible. And so I think, well, and I don't believe sort of quantitative results, but I believe sort of the signs. And we also did a bunch of other simulations with less intense and the same temporal kind of characteristics showed up. So and basically what's happening is if you cool the ocean relative to the land, you cool the air mass above the ocean relative to the air mass above land. And since air increases density as it cools, you end up with the air tends to subside. It tends to induce a subsiding flow over land and a tendency towards air going up subsiding over ocean and going up over land. And if you think of places like the Sahara where you don't have any clouds, it's because that's where the Hadley cell is descending, and so you're having this dry air from high in the atmosphere descending. And so, but you have this tendency towards descending air of the oceans. You lose lots of clouds over the ocean, and now you're no longer presenting white, cloudy surface to the sky, but you're presenting dark ocean surface, and so basically you greatly increase the warming of the planet due to this dark exposure. And then this, by the way, this is the warming under RCP 8.5, and so you can, this is like several times more in amplitude than, say, at least twice the RCP 8.5 is the cooling potential, but you can't sustain it. And even the RCP 8.5, you end up being warmer than you were before. And also the carbon flux is interesting. Yeah, one of the things, people always subtract out their control simulations and just show the delta control. And this is the CSM NCAR-C model control simulation. And they have like a gigaton of CO2 going into carbon going into the ocean in the control simulation. So it's not really spun up, even though it's the advertised spun up ocean. But anyway, so let's pretend that's zero. So what happens with the pipes is basically the same thing that Ashley's found, that you start mixing up this deep CO2-rich water, and then the nutrient utilization goes down, and you end up putting carbon into the atmosphere, not out of the atmosphere. But in the case of RCP 8.5, where you have lots of atmospheric CO2, because there's a higher concentration of excess CO2 at the top of the ocean, it starts putting those down deep, and that eventually overwhelms. And you end up getting an influx. But as you saw, the temperature curves I showed you before, this is like swamped by those sort of direct albedo effects. Over in, I think, Reading, Jonathan Gregory has, in 2004, published this, and colleagues published a great paper in Geophysical Research Letters looking at this way of thinking about radiative forcing from transient climate simulations, where you plot the top of atmosphere imbalance versus surface temperature, and the slope of this line gives you some indication of the climate sensitivity parameter, and the magnitude of this offset from zero gives you an estimate of the effect of radiative forcing. And so so we could say, if you do this ocean mixing and you remove the clouds, that presentation of that dark ocean surface is something like 16 watts of effective radiative forcing, which is like 4 times what a CO2 doubling is. And so this is, I thought, from a climate science point of view, this was kind of fun, because this is the first paper I know where there's a huge effective radiative forcing from something that doesn't directly affect the atmosphere at all. The only thing you're changing is processes in the ocean interior, but you're getting an effective radiative forcing something like 4 times as big as the CO2 doubling. So anyway, that's just sort of a fun thing. The other thing I have to say, I don't really want to go through this story, but I'm actually a co-inventor on some ocean pipes thing. I'm on some patents, so we had to actually do a conflict of interest thing on this paper, and but our basic conclusion was that these ocean pipes were trying to affect global cooling isn't that great an idea, and so it sort of works against my economic interest insofar as there is one there. So anyway, so another sort of crazy thing, there's this organization, ICE 911, and others who've suggested, that methane might pour out of the Siberian permafrost, and so maybe we could sort of whiten the ocean around the Arctic and regrow the ice and cool the Arctic and prevent this Siberia from degassing. So we looked at this idea of, could whitening the ocean around the Arctic save Siberian permafrost? And so, this is a polar view, and so we did one simulation. Where we whitened the ocean in this whole area, so north of 70 degrees, and then we did a whole other simulations, but the two others I'll sort of focus on. Then we did one where what if you just did a poleward of 80 degrees, and then to sort of the test linearity, we looked at one where you just did 80 to 90 to see is doing 70 to 90 the same as 70 to 80 plus 80 to 90. So anyway. So the basic story is, so this is in an abrupt 4x CO2, so in a 4 times CO2 world. So the sea ice extent in the base state of the model is this black line, and the 4 times CO2 is this red line. And so basically doing all these things, you could get some sea ice to grow back, but not all. And that basically 4 times CO2 is a lot of CO2, and so the air is coming from the south is warm, and then you have ocean heat flux, and so on. So, so I have more cases here, but the 3 that I showed you, this is like to the 70 degrees, 80 degrees. That when you first do it, the sea ice is melted back because you have high CO2. You change a lot of surface albedo, and then some ice grows back. And so initially, for each square kilometer of ocean that gets whitened, you get more or less a half a kilometer of sea ice back, and so, but then to maintain that, since you've gotten half a kilometer of sea ice, you only have to whiten half a kilometer. So eventually, you kind of get efficiency is more or less in this model. You get sort of 3/4 of a square kilometer for each kilometer that you're modifying, but to do this, you'd make any climatic difference at all, you'd have to do like many, many millions of square kilometers. So, in each million square kilometers, this is a square 1,000 kilometers by 1,000 kilometers. And, so if the amount of sea ice lost is like 6 million square kilometers, and let's say you have to do, anyway, you're talking about this, just to get the idea, we have some numbers here, right? So, yeah, the altered area is on the orders of, so each of these is a square 1,000 kilometers by 1,000 kilometers. So again, I don't think it's the kind of practical thing, but not only is it not practical, it's not very effective. So, so the temperature change, so there's we looked at 2 things. One is in the Arctic area, which we define 60 to 90, then globally. And more or less, you get some cooling, but it doesn't do that much. A lot of the heat coming to the Arctic is coming from further south, and the Arctic. This is only this area is only less than 7% of the world, because it seems. It says it looks like 30 degrees, and it is 30 degrees, but it's the geometry of the Earth, and so you're only doing a few percent of the planet. And so in terms of planetary cooling, it's pretty ineffective. And then in terms of keeping permafrost, if this is the amount of permafrost at 1 times CO2, and this is what it is at 4 times CO2, the influence into the continental interiors is really pretty small, and so you can sort of prevent a little bit of permafrost loss, but it's not gonna, just in this model anyway, doesn't do very much to preserve permafrost. And so, basically we started looking at the more oddball proposals for geoengineering, and our basic conclusion is both this idea of sort of mixing surface waters for deeper waters, or whitening ocean surface around the Arctic. Neither of them seem particularly feasible or particularly effective at avoiding adverse consequences. So I think I'll just stop there. I have a whole bunch of things, but I'm going to leave with my little favorite little symbol here. So anyway, I can walk through this, but I can just open up for questions. So I'll just open up for questions. Any questions?
Yes, on this last study about sea ice, what does this mean for the ice albedo feedback and the strength of that?
We have a paper on that very topic. Just came out last year. So, so yeah. So, I mean, again, so in the CAM atmosphere model, which is the atmosphere component of the National Center for Atmospheric Research Center model, that we disabled sea ice response in two different ways. One was allowing water to supercool and not freeze, and another one was to just sort of add heat or subtract heat, or basically remove heat to keep the ice in place. And then we looked at what is the climate sensitivity with the ice response and without the ice response. And then also what's the sort of effective radiative forcing from putting sea ice on and off. And so what we found is that the sea ice response more or less adds about 25% to climate sensitivity, or the other way of looking at it, around 20% of the amount of warming is due to the sea ice response. And that the total sort of maximum radiative forcing, effective radiative forcing from like removing sea ice is a little over 3 watts per square meter, so a little less than a doubling of CO2. And so what?
Yeah. So why are the results that you do here then so different from that? So what's the difference then between?
Yeah. Well, the main thing is you're not really getting that much sea ice back. I mean, there's two. Yeah. I guess one thing here. Yeah. Just going back to here, you know. You're only getting another, say 2 or 3 million square kilometers of sea ice, and it's, so let's just even say that the 12 million square kilometers was 3 watts per square meter. I'm just doing this in my head now. And so let's say every 4 square kilometers, like 1 watt per square meter. Yeah, so then you'd expect this to maybe be something like a half a watt or 0.6 watt or something like that. So, I mean, it's something, but it's just not enough to make a huge difference globally. I don't know. I mean, the other thing is there might be some cloud interactions going on that are complicated or something that we're not. I don't know. I don't know. In other words, it could be also some dynamical response that's making it less effective. I don't really know. Sorry.
Has looking at governance research given you any insights into what governance deployments might actually look like?
Well, maybe this is an American perspective, but if you consider the Iraq War as a case example of how international governance works, or maybe Russia in the Ukraine, that I think what you do is you establish international norms and regulations and things saying don't do this without some international consensus, and then eventually some big powerful country thinks it's in their self-interest and they just do it. I mean, I'm a climate scientist, not a governance expert, but so I think that their international norms and laws can act as a restraint on people and increase the cost of acting belligerently. But I think the unfortunate evidence is that when big, powerful countries think something's in their national interest, they often act in their perceived self-interest instead of the broader interest. That's a cynical view. But I don't pretend, that's just my own personal view, and I don't pretend to be an expert on governance. Yeah?
Yeah, you mentioned kind of aerosols in the stratosphere option, not looking on the face of it too bad, and
Yeah.
in terms of impact on crops, similarly really bad. I was just trying to work out, I should know the answer to this probably, but the rest of the time in the stratosphere is about a year. I presume the way it gets removed is it gets transferred, mixed into the troposphere, and then it rains out.
Right.
So how does the amount of aerosol you're assuming compare to the amount of aerosol that we currently emit in the troposphere that we know has kind of impact on the biosphere as well?
Yeah, I mean, the amounts that, for say a doubling of CO2 is a few percent of what's currently coming out of power plants. And so, so you could imagine a scenario where China, I mean, I'm not saying this is plausible, you could imagine a scenario where China wants to not change its radiative forcing while it's cleaning up its sulfur emissions. And the residence time of tropospheric sulfates are something like 5 days or a week or something like that, and stratospheric is like a year and a half. And because of the cloud and different cloud interactions, it's not one for one, but that idea that there might be a factor of 50 or something like that. So maybe for every 50 power plants you close down, you'd have to put one of those power plants worth of sulfur in the stratosphere. It might be sort of the same order. And so it is an acid rain issue, but one that's, more than an order of magnitude smaller than the current acid rain issue.
Yeah, I'd like to challenge your confidence about the growth of crops in another direction.
Okay.
Which is crops do actually rely on sunlight to photosynthesize. And there's been extraordinary little research on this actually. The Ross Society report contained only one sentence that I could find on the subject, and that one sentence, by the way, was incorrect. This seems to be an area we would need to know more about, because I mean, the first order, you cut down the sunlight by a certain percentage, you cut down productivity by a certain percentage.
Yeah, so first of all, I don't pretend to be an expert, but after Mount Pinatubo, if you look at there's carbon isotoping and other evidence of increased biomass growth, and it's thought that the principal action was increased. So with Mount Pinatubo, it reflected around 2% of incoming sunlight, but converted about 20% of incoming sunlight from direct to diffuse radiation. And it's thought that while the top leaves of the forest canopies got less sunlight, that the lower leaves, because of the increased diffuse radiation, the lower leaves got more, and and that as a result there was more carbon uptake. So the other question, a lot of these things have to do with what do you count as your baseline. So some people want to emphasize the imperfection of the offsetting. And so if you, so let's say you're going to have CO2 fertilization, right? So I guess let's say there's three effects. There's sort of CO2 fertilization, just to simplify things, CO2 fertilization, temperature, and sunlight. And so one question is, does the change in respiration rates, how does that vary? But my sense is that most models have a fairly linear, at the ecosystem scale, have a fairly linear response to sunlight. And so other things equal, if you just turn down the sun 2%, you'll lose 2% of photosynthesis, something like this. And then, and usually the CO2 fertilization effect is bigger than that in most models. And so in most models, if the question is added CO2 and reduced sun versus low CO2, low sun, you get more NPP, net primary productivity, with more CO2, more sun. But but that's not the situation that policymakers can be faced, because you're going to have high CO2. And then the question is, well, what does change in aerosols do? And then the trade-off is really this question of, well, direct versus diffuse radiation, reduction in direct radiation, and then what's the importance of temperature and respiration rates. And actually, I was, if I was to say, like, what's a good solar geoengineering experiment to do, it would be interesting. What does the increased diffuse radiation do to, I'm almost thinking like you could put a plastic sheet up somewhere and increase the diffuse radiation and keep it there, and you would expect the understory to grow more, and that, over time will have ecological consequences, because probably lots of ecosystems depend on the tree, its seedlings, not to have to compete with all kinds of other things in the understory. And so, I think all these questions are suitable research areas, and then there just becomes the question of, is that where you want to spend your research dollars, or is there someplace better to spend it?
A quick one on the hydrological cycle. So if the aerosols in the stratosphere are injected in a way that ends up with a non-homogeneous distribution, as I guess there can be implications for
it's been discussed in the science sphere, but is the quality taken that into account? Because there will be losers and winners.
Yeah, so, my sense is that this winners and losers meme, well, not strictly false, has been way overplayed. And there was a paper about this moving the ITCC, but that was a very non-uniform distribution of aerosols used in that paper. And my basic, if you take the catastrophic, I think it's basically, if you take sort of the catastrophic situation, I think it's going to either more or less work and everyone will get better off. And some people might be differentially benefited relative to other people, or it's basically going to be a disaster, in which case everybody's going to be worse off, and some people might be differentially worse off than other people. But the idea that it's so closely balanced that some people are going to be better off and some people worse off. If you think of the 2008-9 subprime mortgage crisis, that resulted in a 5% loss of GDP. And even though it was like in the United States and Ireland and a few other places, we're so economically linked that there was this international economic crisis. And so, I think this idea that the benefits and the costs will be so closely balanced that really some places are going to benefit while some places do worse. And that's not to say there might not be some small places that really aren't. But I think really the better way to think about it is either it's going to basically help to avert a crisis, in which case most people are going to benefit, or it's going to not work. And then almost everybody's going to be worse off. But that in both of those cases, it's not going to be evenly distributed. So I think it's, and this actually, maybe I actually have something on this with Kate Rickey. I did different, I don't want to go too much time, but we did some equity study things of, like what if you don't want anybody to be worse off, and different metrics. But let me go through, so I have Kate Rickey's stuff with me. Yeah, so this is one thing. So this was using some basic thing. This is with the paper with Kate. And this was on minimizing, using a standard kind of damage function, which is, admittedly absurd. And it's just taking the variability normalized temperature change squared plus the variability normalized precipitation change squared, and then trying to minimize that on a regional basis. And this is sort of like how this damage function comes out. And so more or less it says on that kind of damage function you could reduce the total amount of damage by 90%. And then more or less on this, with this optical depth they wanted around 0.2. And, but if you see what the range of, this is this coalition's paper, if you see what the actual range of this damage functions people wanted, some people wanted 10% less and some people wanted 10% more. Now, I don't think that's the way the real world's going to be. I think some people are going to want anything and some people are going to want it all. But, but this idea that, that basically everybody's better off with it. Put it this way, if you just took 0.2 and you believe this damage function, everybody's better off with 0.2 than with 0. And the idea that there's going to be huge wars over whether it's 0.18 or 0.2 or 0.22, I don't believe it. But what I can believe is that plenty of people will say, no, don't do it, make it 0, and then there'll be other people who say, let's do it. So I think among the people who say, let's do it, I don't think the problem is going to be over fine-tuning knobs. I think it's going to be whether you do it at all. But again, that's just me speculating. I have no knowledge. Anything else? Yeah.
So what would you say is the biggest risk of solar geoengineering? How could they most spectacularly wrong?
Well, Earth's system is extremely complicated, and I think we could be sure if we toy with it in some big major way that things are going to happen that we don't anticipate, and that there's a good chance that many of those things will be bad. Right? So I think that's one thing. The other thing is the end game. We have to transform our energy system into one that doesn't use the sky as a waste dump, and that and the end game of ramping up greenhouse gas concentrations, and then you're ramping up some stratospheric aerosol layer, you know that's got to wind up in some bad place. And then once you've sort of come to the conclusion, well, even it doesn't, and I've seen, once you've come to the conclusion, like, even if this worked, at sort of some level, this century, it doesn't get you out of the need to transform your energy system. You know, it makes you say just transform the energy system. But, you know, I mean, it could have, yes, you know, this idea that, well, maybe it's going to have subtle but ultimately profound effects on ecosystems and yeah, so I would say one of the things I'm not so concerned about is this sort of people talking about termination risk, which we actually did the first paper on that one, and that's something I'm not worried about because I think when there's strong incentive to keep doing something, people keep doing it. And so I would say it's just, my basic feeling is the more we interfere with Earth's system functioning, the more problems we're likely to produce, and that the risk-averse path is to avoid interference. And so, but I don't really have any guess about what it is that would actually bite us, but I'm sure something will.
I'll think on that one.
Okay.